In question 16, we need to solve this polynomial equation. So to do that, we can first find the possible rational roots using our p and our q, which is 1 if it's not written. So the possible roots that we could have here would be any of the positive or negative factors of 15. So 1, 3, 5, and 15. And so to have us understand what the answer could be, let's use Descartes' rule. So we see we start with a positive, then go negative, then positive, then negative. Which looks like 3 sign changes. This means we could have 3 positive roots or 1 positive root. Again, since we don't have that many roots right here, we don't have to look for negative roots. So let's go ahead and use some synthetic division, and let's test out the easiest number, 1. If we test out 1, we're going to get 1, negative 6, 6, 11, 11, negative 4, which tells us that 1 is not a root, but it also shows us that we're changing signs every answer in our result. That means that we have a lower bound. This is extraordinarily helpful because we know that our possible roots cannot be any of the negatives. And so since we've already tested 1, we only need to look at 3, 5, and 15 to find 1 or 3 of our remaining roots. So let's go ahead and test 3, since it's the second easiest number after 1 to test. And so we get 1, 3, negative 4, 12, 5, 15, and 0. Well, look at that. 3 is definitely one of our roots. And that allows us to rewrite this equation. We can write x minus 3 times, remember we get the rest of our polynomial from our product or our quotient down here. So we get x squared minus 4x plus 5 all equal to 0. Remember, that's what our equation was equal to. And so right now we have one more parentheses that we need to work out. X minus 3 already shows us that we have an answer of x equals 3. But our second parentheses here, unfortunately, is not factorable. I don't know any numbers that multiply to positive 5 and add to negative 4. So we can use the quadratic formula to solve the second quadratic equation. So let's do that. And I'm going to speed up the video since this should be reviewed. All right, looks like we found our 2 other solutions. So we're going to have a real solution, an x equals 3. We're going to have 2 plus I as a complex solution. And we're going to have its conjugate, x equals 2 minus I. Again, that should fit our fundamental theorem of algebra, which states that we should have 3 roots in total. Again, remember, that doesn't specify whether we have positive, negative, or complex roots, but we've solved for them here. This would be your answer.